Okay, this is a walkthrough of P1, June 2013, and it's the foundation paper. Remember, on the front it tells you what you're going to need and what you already be given in the exam. So you're going to need a ruler and a calculator, and you're going to be given the physics equation sheet. You're allowed an hour, as you are for all science exams, and remember that the only question you're going to be marked on for your specialist vocabulary and your spelling and your organising your information clearly is question 9A. The other ones, don't worry if it's easier to bullet point. Okay, right, let's get started. So, question 1. The pie chart shows the proportions of electricity generated in the UK from different energy sources in 2010. Calculate the percentage of electricity generated using fossil fuels. Okay, so we need to know that fossil fuels is gas and coal, so we need to add those two together. So it'll be 34 plus 43, so coal and gas, and that's going to give us 77%. So we'll put that on there. Okay, right. This pie chart shows that 7% of electricity was generated using renewable energy sources. Which one of the following is not a renewable energy source? And that would be oil. Solar and wind, we know that they can be renewable forms of energy. Complete the following sentence. In some types of power station, fossil fuels are burned to heat something to produce steam. Well, if we heat water, we produce steam. So the answer there would be water. Burning fossil fuels releases carbon dioxide into the atmosphere. Why do many scientists think adding carbon dioxide to the atmosphere is harmful to the environment? Well, we think it causes global warming. Okay. The main cause of acid rain is sulfur dioxide, so it's not going to that one. And visual pollution might be things like quarrying, for example, or turbines, that sort of thing. But it's global warming is linked to carbon dioxide pollution. Right, on to question 2. Okay, diagram 1 shows 4 of the 7 types of wave in the electromagnetic spectrum. So we've got some letters and we've got visible light, infrared, microwaves, radio waves. The 4 types of electromagnetic wave named in diagram 1 above are useful for communication. We've got 2 diagrams here. Which type of electromagnetic wave is used when a traffic signal communicates with a car driver? So, well, this car driver can see it, so it's a visual or visible light. Okay. Which type of electromagnetic wave is used to communicate with a satellite in space? So here we can see that signal going through space, so that's going to need to use a microwave. Gamma rays are part of the electromagnetic spectrum. Which letter, J, K or L, shows the position of gamma rays in the electromagnetic spectrum? Draw a ring around the correct answer. So let's go back up to the spectrum. Well, gamma rays are at the opposite end. So this is really short wavelength getting to really longer wavelengths at this end. So J is going to be gamma rays, okay? I'd recommend that you label it up and try and have a rhyme or something to help you remember the order of this, because it's a common question to pick out a missing gap in the electromagnetic spectrum. So we're going to say J is gamma rays. Okay, diagram 2 shows an infrared wave, and here we can see a transverse wave, okay, labelled. Which one of the arrows labelled A, B or C shows the wavelength of the wave? Write the correct answer, A, B or C in the box. Well, the wavelength is B here. A is the amplitude, so as the sound gets louder, that will get much bigger, and if it's a quieter noise, it will get much smaller. Wavelength is linked to pitch, so if it's a squeaky noise, if this is a sound wave, we get a much shorter wavelength, and a deeper noise would be a longer wavelength. Right, draw a ring around the correct answer to complete sentence. The wavelength of infrared waves is shorter than, the same as, or longer than the wavelength of radio waves. So if we come back over here, infrared waves are there, radio waves are there. Well, radio waves have the largest wavelength and gamma rays have the shortest wavelength. So infrared waves are shorter than radio waves. Okay, they're shorter than the wavelength of radio waves. On to the next bit. So mobile phone networks send signals using microwaves. Some people think that the energy a person's head absorbs when using a mobile phone may be harmful to health. Scientists have compared the health of people who use mobile phones with the health of people who do not use mobile phones. Which one of the following statements gives a reason why scientists have done this? Tick one box. Have they done it to find out if using a mobile phone is harmful to health, to find out if mobile phones give out radiation, or to find out why some people are healthy? So the reason they have compared the health of people who use mobile phones with the health of people who do not use mobile phones is to find out if a mobile phone is harmful to health. Okay, the table gives a specific absorption rate, or SAR, value for two different mobile phones. The SAR value is a measure of the maximum energy a person's head absorbs when a mobile phone is used. So they've got mobile phone X and Y and the SAR value. Okay, so 0.2 and 1.35. A parent buys mobile phone X for her daughter. Using the information in the table suggests while buying mobile phone X was the best choice, and this is worth 2 marks. So the first thing we can see that X has the lower SAR value, okay, and that's the measure of the maximum energy a person's head absorbs when a mobile phone is used. So it has the lower SAR value, which means it is the least likely to cause harm or cause her health, any problems on her health. Okay, there's a lower SAR value, which means it's least likely to cause harm. Okay, on to question 3. Okay, a person can see an image of himself in a tall plane mirror. So we've got the person, we've got a plane mirror, and we've got a point over here labelled C. The diagram shows how the person can see his hat. Which point, A, B or C, shows the position of the image of his hat? Write the correct answer, A, B or C, in the box. So the image of his hat will be over here at C. Okay. On the diagram, use a ruler to draw a light ray to show how the person can see his shoe. So he's got to be able to see it as a reflection in the mirror. Okay, we're not talking about his hat anymore, so we can ignore C altogether, so don't get confused by this over here. So we know that the light must bounce off his shoe onto the mirror and back into his eye, and we need to make sure the angles are about the same. So what you want to do is put your normal line roughly halfway between his eye and his shoe. So if we go somewhere along here, okay, and we want to draw a line. So again, remember on the front it said we needed to use a ruler, and you can see why now. A line from his shoe to the mirror with an arrow on it to show direction of travel, and then a line from the point there up to his eye to show how light has travelled. Now these angles should be about the same, so if you want to take a protractor and then redraw and bring that line down slightly lower to increase that angle, then that would be fine as well. The examiner will only judge the angle by eye. He will not measure it with a protractor, so you need to make sure that you've roughly drawn it correctly, okay? So you're going to get a mark for the reflection, you're going to get a mark to check these angles are the same, and that we get the arrows labelled as well to show the direction of travel, okay? Right, which one of the words in the box is used to describe the image formed by a plane mirror? Is it imaginary, real or virtual? We don't imagine it to be there. It's certainly not real because it's an image formed in a mirror. We call it virtual. Okay, so it's a virtual image. Right, on to question 4. Okay, question 4. A student investigated how the number of blades on a wind turbine affects the output voltage of the turbine. The student used the apparatus shown in the diagram. So we can see a fan, a wind turbine, the clamp stand, and the fan is attached to a voltmeter, and we can see a meter ruler. The fan was used to turn the turbine. The fan was always the same distance from the turbine. Why? Well, we only want one independent variable, one thing we're changing, okay, and that's going to be the number of blades, because I said up here the investigator how the number of blades on a wind turbine affects the output voltage. So we say only one independent variable. We can say that changing the distance might change that voltmeter reading, so it might not make it fair. I think if we put, so they only had one independent variable, which was number of blades, and that would be a good answer there because we've used our sort of ISO language. After switching the fan on, the student waited 20 seconds before taking the voltmeter reading. Suggest why. Well, they might have left it 20 seconds so it can get to a steady, the fan can get to a steady speed, and they make sure it's a fair reading. Okay, so the fan can reach a steady speed. Okay, right. The student changed the number of blades on the wind turbine, and the student's results are shown in the scatter graph. So we can see that the output voltage in volts and the number of blades along the bottom, and we can see that as they increase the number of blades, we got an increase in the output voltage. What conclusions can be made from the results in the scatter graph? Well, we can see exactly what I've just said, the conclusion, as the number of blades increases, so does the output voltage. Okay, importantly, I've used the terms that are on the labels on the graph. I've not changed them, I've not tried to change them at all into my own language. I've used them directly as they are. That's worth 2 marks. So I'm going to put some data or reference the graph in a little bit more detail. So I think for this one, I can see that it's increased up here and then it becomes fairly constant. Okay, so we can see, however, there is little change in output voltage for 4 to 6 blades. Okay, they're all pretty much the same. Okay, for part B. The amount of electricity generated using wind turbines is increasing. Which graph, A, B or C, is most likely to show the electrical power output from a wind turbine over one day? So we've got graph A, power output staying constant. Graph B, again staying constant there, but dropping. In fact, it's not got labels there. That's 0, 12 noon and the end. So we've got constant power there, and then this one here where the power's changing. Write the correct answer, A, B or C, in the box. Well, if it's a wind turbine, we know that wind turbines will only work when it's windy, and that's going to change throughout the day. So we're going to go for graph C. Okay, and give a reason for your answer, because wind speed varies. Okay, so it varies throughout the day, or wind speed varies is sufficient for the answer there. Okay, on to question 5. Okay, a lorry has an air horn. The air horn produces sound waves in the air. Use one word to complete the following sentence. Sound waves cause air particles to vibrate. The air horn produces sound waves at a constant frequency of 420 Hz. The wavelength of the sound waves is 0.80 meters. Calculate the speed of the sound of waves. Use the correct equation from physics equation sheet. So we're looking for something with frequency and wavelength and speed. So let's have a look if we can find that on here. So we've got here speed, frequency and wavelength. So we're going to use this calculation. So first thing I'm going to do is write it out so I don't forget what I'm doing. So there is my equation from the equation sheet. I need to find speed, and look at it, it's written in the same way. So we can see that V equals speed. So I don't need to rearrange. So V equals frequency, 420, as it's told me there, times the wavelength, which is 0.80 meters. So if I do that calculation, I get 336 as my speed. So I'm going to write that in down there, 336. Remember, that's an easy 2 marks there, just using your calculation sheet. Please make sure you've got a calculator in the exam. A person standing at the side of the road as a lorry goes past hears a sound from the air horn change pitch. What determines the pitch of a sound? Well, the pitch of the sound, if you think of your wave again, okay, there's a standard wave. If it's higher pitch, this wavelength is going to decrease. So a higher pitch sound would look more like this. Okay, same height, same volume, amplitude's not changing. So I'm getting more waves in the same space, so I'm changing frequency. Okay, so frequency is the answer there. As the lorry moves away from the person, the air horn continues to produce sound waves with a wavelength of 0.80 meters. What is the wavelength of the sound waves the person's heard? Draw a ring around the correct answer. So as that sound goes away, this is the Doppler effect that we're talking about here. So if this is our person, as it comes towards them, that sound wave is shorter, and then as it moves away from that person, these sound waves get longer and longer. Okay, so as it's travelling away, so the pitch is going to decrease, so the answer is going to be longer than 0.8 meters. The sound waves a person's heard from the moving air horn are different to sound waves the air horn produced. What is the name given to this effect? And that is the Doppler effect. Okay, a little bit like the redshift and blue shift we see in space, when we can see that the wavelength's decreasing and increasing. Okay, on to question 6. Okay, a student used the apparatus drawn below to investigate the heating effect of an electric heater. So here we can see an electric heater, a thermometer and a metal block and a power supply. Before starting the experiment, the student drew graph A. Graph A shows how the student expected the temperature of the metal block to change after the heater was switched on. So they thought that the increase in temperature of the metal block in degrees C and the time in seconds, and that the temperature would increase. Describe the pattern shown in graph A for 2 marks. Okay, so we can see that as the time increases, we also get an increase in temperature of metal block, but it's a straight line, which means it's directly proportional, and this is what you're going to get for your 2 marks. So temperature and time switched on are directly proportional. Okay, and that is what will get you your 2 marks, talking about the effect or describing the pattern in detail. Okay, 6A part 2. The student measured the room temperature. He then switched the heater on and measured the temperature of the block of the metal, or the temperature of the metal block every 50 seconds. The student calculated the increase in temperature of the metal block and plotted graph B. So we can see that we've now got a curve this time rather than a straight line. After 300 seconds, graph B shows the increase in temperature of the metal block is lower than the increase in temperature expected from graph A. So you can see that it's reached about 32 on here, okay, looking at the scale, whereas over here at 300 it had reached about 37, 38. So suggest one reason why that it's lower. Well, we can talk about the energy transfer, that we might get some energy loss to the surroundings to warm up the room. We've also got to warm up the heater, we've got to warm up the thermometer as well. So suggest one reason why. We can say the energy might be transferred to the surroundings. So you know, it wasn't insulated, so we can suggest that it might have been lost to the surroundings as heat. Okay, the power of the electric heater is 50 watts. Calculate the energy transferred to the heater from electrical supply in 300 seconds. Use the correct equation from the physics equation sheet. So I've got power, I've got time, and I need energy transferred. Let's have a look at the equation sheet, which one we want to use. Well, here I've got energy transferred, power and time. So I'm going to use E equals P times T. So E equals P times T. I want to find energy transferred, so I don't need to rearrange. So E equals power, which is 50, times time, which is 300. And I do need this in seconds, so I don't need to change that into units at all. And that's going to give me 15,000, so I can put that in here as my answer to that question. Okay, on to the next question. 6b. The student uses the same heater to heat blocks of different metals. Each time the heater is switched on for 300 seconds. Each block of metal has the same mass but a different specific heat capacity. So aluminium has 900, iron 450 and lead 130. Which one of the metals will heat up the most? Draw a ring around the correct answer. Now the answer you want here is lead, because it needs less energy to heat up. So this aluminium needs 900 joules per kilograms of degrees C. So specific heat capacity is much higher for aluminium. Okay, so you're going to have to use much more energy to heat that to the same temperature than lead. So this one, lead, is going to heat up much faster because it has the lowest specific heat capacity. And give in terms of the amount of energy needed to heat the block a reason for your answer. Well, lead needs the least amount of energy to raise the temperature, and I'm going to put by 1 degree C, because this is the amount of energy needed to heat a certain mass by 1 degree C. Okay, so I'm going to add that in there as well, just to cover my back, to make sure I get the mark there. Right, a homeowner uses an electric immersion heater to heat the water in his hot water tank. The hot water tank has no insulation. So see, cold water in, the electric immersion heater, copper wall and heat out at the top, or hot water out at the top. Draw a ring around the correct answer to complete each sentence. Energy is transferred through the water by conduction, convection or evaporation. Well, I'm still getting water in and out, so I'm not evaporating anything, so it's not going to be that one. I can't do conduction because conduction has to be a metal, so things don't move. So it's through the water by convection, because water can move around, and convection, you get the convection current cycling all around. So particles need to move. That can only happen in a liquid or gas. Energy is transferred through the copper wall of the hot water tank by conduction. That's how heat transfers through a metal. Okay. To keep the water in the tank hot for longer, the homeowner fits an insulating jacket around the tank. The insulating jacket costs £12 to buy. The homeowner expects to save £16 each year from reduced energy bills. Calculate the payback time for the insulating jacket. So what we need to work out is how quickly they will recuperate their money from the £12 they've had to spend, and they want the payback time in years. Okay, so we can see that they think they're going to save £16 each year, and the insulating jacket costs £12. So we can already see it's going to take them less than a year to buy it back. Okay, so let's see if we can work out a number, and we can work out the right answer. We can double check, because we should be expecting our answer to be less than 1 year. So what we're going to do is we are going to take the amount of how much it's cost, and we're going to divide it by the time it's how much they expect to save per year. So we're going to do 12 divided by 16, and that's going to give us 0.75. So you could write 0.75, or you could put 3/4 of a year, or 0.75. Either would be absolutely fine for your answer. Or you could have put 9 months, but again, it has said years in the question, so I think that's probably just watch your back if you're going to do that, although you would have been given the marks for it anyway. But 0.75 or 3/4 of a year. Okay, on to question 7. So question 1. The Sankey diagrams show the energy transfers in a traditional coal burning power station and a combined heat and power station, or CHP station. So here we can see we've got input energy from fuel, which is this whole bit here, and then this amount comes off as electricity, but we've got this much coming off as wasted. So we've got quite a large amount of wasted energy there. And the CHP station, we've got the same input. So if you think 1, 2, 3, 4 boxes, okay, larger boxes, that's the same there. We've got some coming off as electricity, some coming off as energy used to heat local homes, offices and factories, and then quite a small amount of wasted energy. So if you compare the two, we can see straight away this has got far less wasted than this one here. What effect does the waste energy from a power station have on the surroundings? So what we should know is that this waste energy will basically just warm up the surroundings. So it will warm it up. Okay, that's what waste energy does, is it just warms up the surroundings. Right, calculate the efficiency of the CHP station using the correct equation from the physics equation sheet. Now the key word here is efficiency. So if we look at our data sheet, we've got two calculations that's got efficiency. We need to think about which one we need to use. The difference is this one has energy and that one has power. So if we have a look at our sheet, what's included here, well, it's using the words energy in our Sankey diagrams, so we're going to use this equation here. Okay, so what we want is we want useful energy out divided by total energy in multiplied by 100. Okay, so if we write this down here, so we want useful energy out divided by total energy in. So our useful energy out, and we're looking at the CHP station, we've got all of this here, okay? So on this side, this equates to 100%, okay? So this would be 100% of electricity going in. And we need to work out what these squares add up to. So we can literally just add up the squares and work it out from that, or we can do it as a percentage. So we've got 1, 2, 3, 4, 5 small squares in each box, larger box. So 5, 10, 15, 20 is our input energy in. And on this side over here, we've got 1, 2, 3, 4, 5, 6, 7 plus 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so what we've got is 16 divided by 20, and that would give us 0.8, and then we need to times that by 100. Remember here on our equation sheet we need to multiply it by 100, and that would then give us 80%. Okay, so 80% efficiency. If you'd left it as 0.8, that would have been absolutely fine. You would have got the marks for that. It wouldn't have been a problem. Or you could have converted it to the percentage as 80%. Okay, right, on to part C. Why is a CHP station more efficient than a traditional coal burning power station? So have a think. So if we have a look, it is much more efficient. There's a huge amount of waste energy here and a very small amount there. So what we can say is that some of the electricity or energy that would have been wasted over here, okay, has actually been used successfully and usefully to heat local homes, offices and factories. Okay, so that's all we're going to say, is that some of the energy that would have been wasted on this side has actually been used usefully on this side. So we have useful or wasted energy, and it's been used usefully. So we can say that some of the energy that would be wasted in the coal burning power station has been used usefully in the CHP station. You could say how, you could say for heating homes, etc. But it's this bit that has been used usefully, it's really important. Okay, a CHP station is usually used to meet the demand for electricity within the local area. The electricity is not transmitted and distributed through a national grid. What is a national grid? Right, the national grid is just the cables and transformers. Okay, it isn't the pylons and it's not the power stations. It's that section in the middle that we're talking about when we talk about the national grid. Make sure you know that's a very, very common exam question. Using electricity locally and not transmitting it through the national grid increases the overall efficiency of a CHP station by 7%. Give one reason why. Okay, so what's happening here is because we're not transmitting it through cables, we're not losing energy as the electricity travels through the cable. So as the electricity travels through the cable, we tend to lose energy as heat energy. Okay, but if we're not putting it through the cables, we're not losing that energy. So we can say there's less energy lost or wasted in the shorter cables. Okay, so it's going through cables, but they're significantly shorter than if we'd sent it through the national grid. Okay, on to question 2. Okay, the picture shows a person taking a hot shower. When a person uses the shower, the mirror gets misty. Why? So if it's getting misty, it's condensation, isn't it? The water, the steam, water molecules in the air are condensing on the mirror, and that's why we're getting it as misty. So we need to now explain that process and why that happens. So the first thing that's going to happen is the water evaporates. So from the shower, the water evaporates into steam. Okay, the water molecules then hit the cooler mirror and lose energy. Okay, it's really important. Remember that if we compare a solid, so to a liquid, which the molecules are slightly further apart, and then a gas, which they're really far apart, as it goes along here, it gains energy, okay, and the particles have more kinetic energy, they can move more. If it hits something colder, it loses that energy from being a steam and it goes back to being a liquid again. And if that mirror wasn't as cold, it wouldn't lose the energy and it wouldn't be converted back into a liquid, okay? So it's this idea of losing and gaining energy which gets it to change from a solid to a liquid to a gas and then back again. So water evaporates into steam, water molecules then hit the colder mirror and lose energy. So the water condenses onto the mirror. Okay, or you can say condensation is formed or something like that's absolutely fine. Okay, so there's our 3 marks for that question there. And again, I've just bullet pointed it, found it easier. There's no marks for putting it into a paragraph, but obviously if you prefer to, then that's fine as well. Okay, 2B. The homeowner installs an electrically heated mirror into the shower room. When a person has a shower, the heated mirror does not become misty but stays clear. Why does the mirror stay clear? So exactly what we just said before. If that mirror is warm, then it won't take away the energy that this gas has here. So it won't then encourage it to go back to a liquid. It's not taking that energy away. So we can say that because the mirror is warm, the rate of condensation is reduced. Okay, and if you want to, you could go and talk about energy, but it's only worth 2 marks. So we're just looking at sort of a basic level of detail here. So we'd say because the mirror is warm, the rate of condensation is reduced. And if you think about your specification, and the videos that I've done that link directly to the specification, it talks about the rate of condensation and evaporation increasing and decreasing, and this is exactly the sort of terminology we need to use in this question. Okay, so you can see why it's so important to look at your specifications. Okay, on to question 3. Okay, on to our 6-mark question in this paper. So in this question, you'll be assessed on using good English, organising information clearly, and using specialist terms where appropriate. Remember, the exam board recommended last year in their feedback that students map out an answer on the back page, roughly, and then come back and revisit this when you've got your ideas in your head a bit clearer. So the diagram shows a structure of a vacuum flask, and here we can see we've got some features labelled, which I suggest are going to be quite important for structuring our answer in the 6-mark question. A vacuum flask is designed to reduce the rate of energy transfer by heating processes. Describe how the design of the vacuum flask keeps the liquid hot, or the liquid inside hot. Okay, so we have got some design features labelled. They have labelled a plastic cap, a double-walled glass container, a vacuum, and silvered surfaces. So I think we should have a paragraph on each, and we're describing how the design keeps the liquid hot. So that's the important bit. Okay, so we need to talk about why the plastic cap keeps it warm, etc. So let's go through. So the first, I'm going to bullet point to make it a bit easier, but obviously in the real exam, please do this as a paragraph. So if we talk about the plastic cap and how this helps, this is quite a common exam question as well, so it's worth practicing. So a plastic cap, because it's plastic, it's a poor conductor of heat. So we wouldn't want a metal lid because that would conduct the heat out of the liquid much faster. So that's a poor conductor, okay? We can also say that it stops convection currents forming at the top of the flask because the lid is on, so we can't get any convection current going around. So it's a poor conductor of heat. It also prevents convection currents forming at the neck. Of the bottom, okay? We can say that the liquid can't evaporate because it's got a lid on as well. So we've got no evaporation of liquid. Okay, so we can see that overall we've talked about conduction, convection and evaporation. Okay, so all really important processes. Okay, and here we can see let's mention heating processes in the question. Right, let's talk about the fact it's a glass container now. So the second feature down on the diagram. So the glass container again, glass is a poor conductor. So we'll use less by the process of conduction. So you can say, so reduces conduction, okay? And that is the main one there for the glass, okay, that it's a poor conductor. So let's put conductor. Okay, so reduces conduction. Right, on to the vacuum then and why that is an important feature. Okay, again, check your spelling on vacuum. It's listed there, so no reason why you shouldn't be able to spell it correctly. So because it's a vacuum, it means that conduction and convection can't happen because they require particles to transfer the energy. And because there's no particles, we're not going to have those. So we can say that conduction and convection cannot occur because they need particles. Okay, so it stops energy transfer, let's say between the double wall. No, it's not in the double wall, is it? Between the flask container. Okay, so between the layers of the container there. Right, and let's go on to silvered surfaces. Okay, the silvered surfaces then feature on this layer here where we've got the vacuum, so that edges of the container we just talked about. Okay, so we have to think about why silvered surfaces, light and shiny, might reduce heating processes. Okay, so what they are going to do, if you remember from the first part, they're going to reflect infrared radiation. Okay, so then we're going to back, if you like, into the liquid. It's going to reflect the infrared radiation, and we also know they are poor emitters of infrared, so they're not going to absorb it. Okay, because they're not going to be able to emit it. So we get all of the infrared reflected back towards the liquid. So reflected infrared radiation, poor emitters of infrared. So let's put most of the infrared radiation, which will be heat, is reflected back towards the hot liquid. Okay, so we've covered all the points there in terms of the design. We've talked about plastic cap, glass container, vacuum, silvered surfaces, and we've talked about the processes. So we've talked about conduction, convection, radiation, evaporation. So the clue was in the question in terms of how we wanted to word it. Okay, but it is a common question, this one, showing you a flask and then asking you to talk about it. So it's one worth recapping or going over the processes if you're not familiar. Right, on to part B. So we've got Arctic foxes live in a very cold environment. Arctic foxes have small ears. How does the size of the ear help to keep the fox warm in a cold environment? So again, a little bit like biology, make sure you know what the question is asking you. So it's mentioned small ears, but it's asked us how they're going to help keep the fox warm. Okay, nothing to do with predation or anything else. It's about keeping it warm. So the fact they have small ears, those small ears means a small surface area. So what we're going to do is reduce the amount of energy transferred from the fox to the outside. Okay, so we can say, so therefore reducing energy transferred to the environment. Okay, so we talked about small surface area and transfer of energy. Right, on to question 5.